Bonding is electrically connecting two or more conductive objects together to equalize their electrical potential. Grounding is connecting a conductive object to the earth, which is considered to have a voltage of 0 volts. In the case of the water line, it is bonded to the electrical system, not grounded. This is because the water line is already grounded through the earth. The purpose of bonding the water line to the electrical system is to ensure that all conductive objects in the building are at the same electrical potential. This helps to prevent electrical shocks and fires. The water line is often chosen as the bonding point because it is a long, continuous conductor that runs underground and is in contact with the earth for a significant distance. A grounding rod is only necessary if the electrical system is not already grounded through a water line or other conductive object that is in contact with the earth. Gas lines are not required to be grounded, but they should be bonded to the electrical system. This helps to prevent static electricity buildup and the potential for gas explosions. The grounding of underground bulk tanks in petroleum distribution is not primarily for grounding purposes, but for cathodic protection. Cathodic protection is a method of preventing corrosion by connecting metal structures to a sacrificial anode that corrodes instead of the protected structure. Now let's delve deeper into the specifics of bonding and grounding, particularly as they relate to water lines, gas lines, and electrical systems. In electrical systems, the terms bonding and grounding are often used, but they represent distinct concepts with different purposes. Grounding creates a low impedance path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly trip and energize the circuit. Bonding, on the other hand, ensures that all metallic parts of an electrical system and other conductive materials in a building are at the same electrical potential. This eliminates voltage differences that could cause electric shock hazards. When dealing with a metallic water line that runs at least 10 feet underground from the building, it serves as an excellent grounding electrode. According to electrical codes, a metallic water pipe that is in direct contact with the earth for at least 10 feet is considered a grounding electrode. Bonding the water line to the electrical system helps maintain equipotentiality. It's important to note that the primary function of connecting the water line to the electrical system is bonding, even though the water line itself is grounded through contact with the earth. You are bonding the water line to the electrical system to ensure equipotentiality. Grounding typically refers to connecting the electrical system, specifically the neutral conductor at the service entrance, to a grounding electrode, such as a ground rod, ground plate, or the metallic water line itself. The conductors and appliances are not directly grounded or bonded in the sense of connecting them to the earth. Instead, the metal enclosures of appliances and equipment are bonded together and connected to the grounding system of the building. This ensures that if a fault occurs and a live conductor comes into contact with the metal enclosure, the fault current will safely flow back to the source, tripping the overcurrent protection device. Whether a grounding rod is needed depends on whether the electrical system already has an effective grounding electrode. If a metallic water line that meets the 10-foot requirement is present, it can serve as the primary grounding electrode. In some cases, a supplemental grounding electrode, such as a ground rod, may be required to augment the water line electrode and ensure a low impedance ground path. The National Electrical Code, or NEC, dictates the requirements for grounding and bonding. Gas lines are generally not required to be grounded in the same way as electrical systems. However, gas piping systems should be bonded to the electrical grounding system. This bonding helps to minimize the risk of static electricity buildup, which could potentially ignite natural gas or propane. Bonding gas lines helps equalize the electrical potential between the gas piping and other metallic components in the building, reducing the risk of static discharge. In the petroleum distribution industry, underground bulk tanks are often grounded, primarily for cathodic protection purposes. Cathodic protection is a technique used to prevent corrosion of buried metal structures such as pipelines and storage tanks. The tanks are connected to a sacrificial anode, which corrodes instead of the tank itself. This system requires a good electrical connection between the tank and the anode, which is achieved through grounding. While grounding, the tanks can also provide a path for static electricity dissipation. The primary purpose is corrosion prevention. To summarize, firstly, bonding and grounding are distinct but related concepts in electrical systems. Secondly, bonding ensures equipotentiality, while grounding provides a path for fault current. Thirdly, water lines are bonded to the electrical system to enhance safety. Fourthly, gas lines are bonded to prevent static electricity buildup. Fifthly, grounding of underground tanks in the petroleum industry is primarily for cathodic protection. Let's further elaborate on the specific requirements and considerations for bonding and grounding in various scenarios. When bonding a water line, it's essential to use appropriate bonding clamps and conductors that are sized according to the electrical code. The bonding conductor should be connected to the water line on the customer side of the water meter, as close as practical to the point where the water service enters the building. This ensures that the entire water piping system within the building is effectively bonded. In situations where a non-metallic water pipe is used for a portion of the water service, a supplemental grounding electrode, such as a ground rod, is typically required. This is because the non-metallic pipe breaks the continuity of the metallic water pipe, preventing it from serving as an effective grounding electrode. When installing a ground rod, it should be driven into the earth to a depth of at least 8 feet. The top of the ground rod should be flush with or below ground level to prevent it from being a tripping hazard. The grounding conductor connecting the ground rod to the electrical system should be protected from physical damage by routing it through conduit or using a listed grounding electrode conductor clamp. For gas lines, bonding should be performed using a bonding clamp and conductor that is sized appropriately for the electrical system. The bonding conductor should be connected to the gas piping system on the downstream side of any insulating unions or couplings. This ensures that the entire gas piping system is effectively bonded. In some cases, local codes may require gas lines to be bonded at multiple points to ensure optimal protection. When dealing with cathodic protection systems for underground tanks, it's crucial to follow the manufacturer's instructions and industry best practices for installation and maintenance. The sacrificial anodes should be regularly inspected and replaced as needed to ensure the continued effectiveness of the corrosion protection system. The electrical connections between the tank, the anode, and the grounding system should be checked periodically to verify that they are intact and providing a low resistance path for current flow. It's important to remember that electrical codes and regulations vary depending on the jurisdiction. Always consult with a qualified electrician or electrical inspector to ensure that your bonding and grounding practices comply with the applicable codes in your area. Proper bonding and grounding are essential for ensuring the safety and reliability of electrical systems. By understanding the principles and requirements of bonding and grounding, you can help prevent electrical shocks, fires, and equipment damage. In addition to the points already discussed, it's worth noting that the size of the grounding and bonding conductors is crucial for their effectiveness. The National Electrical Code, or NEC, specifies the minimum size of these conductors based on the size of the service entrance conductors or the rating of the overcurrent protection device. Using undersized grounding or bonding conductors can compromise the safety of the electrical system and may not provide adequate protection in the event of a fault. It's also important to ensure that all connections are made properly and are tight. Loose connections can create resistance, which can impede the flow of fault current and reduce the effectiveness of the grounding and bonding system. Regularly inspect all connections to ensure that they are clean, tight, and free from corrosion. In corrosive environments, it may be necessary to use special corrosion-resistant connectors and conductors to ensure the long-term reliability of the grounding and bonding system. Another important consideration is the type of grounding electrode used. While a metallic water line is often the preferred grounding electrode, it may not always be available or suitable. In such cases, other types of grounding electrodes such as ground rods, ground plates, or concrete encased electrodes may be used. Each type of grounding electrode has its own advantages and disadvantages, and the selection of the appropriate electrode depends on the specific site conditions and the requirements of the electrical code. Ground rods are relatively easy to install and are suitable for most soil conditions. Ground plates provide a larger surface area for contact with the earth and are often used in areas with poor soil conductivity. Concrete encased electrodes, also known as UFA grounds, are installed within the concrete foundation of a building and provide excellent grounding performance. Regardless of the type of grounding electrode used, it's essential to ensure that it is properly installed and connected to the electrical system. The grounding electrode should be located as close as practical to the service entrance and should be accessible for inspection and maintenance. The grounding conductor connecting the grounding electrode to the electrical system should be continuous and unbroken, and should be protected from physical damage. In addition to grounding and bonding, surge protection is another important aspect of electrical safety. Surge protective devices, or SPDs, are designed to protect electronic equipment from voltage surges caused by lightning strikes or power line disturbances. SPD are typically installed at the service entrance and at individual equipment locations to provide comprehensive surge protection. When selecting SPD, it's important to choose devices that are rated for the voltage and current requirements of the electrical system. The SPD should also be listed by recognized testing laboratory, such as Underwriters Laboratories, or ALL, to ensure that they meet safety and performance standards. Regular maintenance of the electrical system is essential for ensuring its continued safety and reliability. This includes inspecting the grounding and bonding system, testing the operation of overcurrent protection devices, and checking for any signs of damage or deterioration. Any problems that are identified should be promptly repaired by a qualified electrician. In summary, firstly, ensure grounding and bonding conductor sizing is code compliant. Secondly, maintain tight and corrosion-free connections. Thirdly, select appropriate grounding electrode types based on site conditions. Fourthly, install surge protection devices to protect against voltage surges. Fifthly, conduct regular maintenance of the electrical system. Understanding and implementing proper bonding and grounding techniques is crucial for creating a safe and reliable electrical system. It's a responsibility that should be taken seriously by homeowners, contractors, and electricians alike.